I'm going to speak today about deceleration using nuclear fusion propulsion. Now, some of this, okay, so why deceleration and not acceleration? Because there are, as Jeff has pointed out over the last couple of days, and Andrew, there are lots of ways to accelerate, okay? There are a lot fewer ways to decelerate when you're far away from the Earth, near the other stars. I think all of us have toyed around with some ideas, but those are probably at a TRL level even lower than this is, which says something. Okay, so the idea is we want to get from the solar system through the heliopause, through the Oort Cloud, through the local interstellar cloud, the G cloud, what I presume to be another Oort cloud around Proxima AB because it has two solar masses. The AB has a combination of two solar masses, roughly. So I would assume there's an Oort cloud here. And of interest is the fact, one interest is the fact that Proxima is orbiting within that Oort cloud. So talking about disturbing an Oort cloud and sending lots of comets into a solar system. So the idea is that we want a spacecraft that could do this in 100 years. Okay, so again, this is 100 years using, now in the past I've given a talk about antimatter. This talk is about nuclear fusion, but the same sort of idea, 10-year acceleration burn, 10-year deceleration burn, 80 years of coasting. And so what are the, if you make those assumptions, what are the requirements? Okay, of course, the biggest requirement is the fact, oops, again, I'm hitting the wrong button. Okay, so the biggest requirement is set by the rocket equation, okay? You have to have an exhaust velocity that's a few percent of the speed of light in order to have a reasonable fuel to dry mass ratio. And we're going to want power along the way because we're going to want to be able to transmit messages, data back to Earth, and we're going to want Earth to be able to update the spacecraft. Because again, over 100 years, we're going to learn a lot also, and we're going to want to update the spacecraft. So anyway, so this is just basic physics, okay? If you say a 10-year burn to get up to a velocity required to have a total of a 100-year mission, those are simple equations, okay? And so first of all, during the acceleration phase, you see that within a year, you're already through the Kuiper belt and you're at the heliopause. A little after 2 years, you're at the gravity lens region. And then within 5 years, you're entering the Oort cloud. So Jeff was just talking about 1,000 AU per year. This is actually 3,000 AU per year at the peak velocity, okay? That's what's necessary to get to Proxima Centauri in 100 years. So, and then as has already been alluded to, we're not aiming at where Proxima and Alpha Centauri AB are right now, but where they're going to be in 100 years, okay? And so 0, 0 is the current position of Proxima Centauri in terms of declination and right ascension, and the dot to the left is where Proxima Centauri will be, okay? And it's a measurable difference. And then the same thing for Alpha Centauri AB. So the sort of basic mission architecture I'm talking about here is a two-stage mission where the first stage is the acceleration that gets you up to 4.7% of the speed of light. Note, we're going at a declination of 62 degrees, so we're toward the south pole of the ecliptic. So we're already out of the ecliptic almost immediately. And so in terms of the Oort cloud image that Jeff just showed, we're in the spherical part. Okay, we're not seeing the disk part in the ecliptic. Okay, and so the idea is that first stage then stops its acceleration burn. There's a question, which star or stars do I aim it at? Do I aim it at Alpha Centauri AB or do I aim it at Proxima Centauri? And we'll get to that in a moment here. And so in the black curve, the first stage is aimed at Alpha Centauri AB. And then for the deceleration burn, the second stage has to make this is a not correct perspective, but it's a relatively sharp angle to now deflect and decelerate simultaneously to get to Proxima Centauri. The alternative, which is the red curve, is that you have your acceleration burn, which is aimed at Proxima, and then at the very end of that burn, you tilt the spacecraft a little bit, the first stage, and you have it deflect, which at a much lower angle now, toward Alpha Centauri AB. And prior to that, you've already disconnected the second stage, and so it keeps coasting and then decelerating to Proxima B. So this is just a summary of sort of the criteria and the mission parameters we're assuming. We have the initial spacecraft, the entire mass is 572 kilograms. The dry masses are 100 kilograms each. The first stage also carries the second stage fuel as a dry mass. And so you go through all these numbers, and you get an initial acceleration of the entire spacecraft at presumably 1 AU if we're launching near the Earth of 0.033 meters per second squared. The solar gravitational acceleration at that point is a factor of 5 smaller. So in the work here, we're just ignoring the sun. We can compensate that along the way. Okay, so there's the acceleration curve for the second stage. So it shares the acceleration with the first stage, long 80-year coast, and then the deceleration. The deceleration and acceleration change with time because the fuel mass is being consumed. And so therefore the spacecraft is getting lighter as it continues the burn. And then to the right, you have the velocity curve. And this is the acceleration due to the sun. So this, at the very top corner there, is your 0.006 meters per second squared. So to do all, okay, so that's just the physics, and that's just based on, I want to get there in 100 years. Okay, I haven't really invoked fusion yet. I could easily have done, I mean, I did do this many meetings ago with antimatter. So up until now, this has sort of been, if you're assuming a rocket equation and some sort of propulsive technique and sort of constant burns, this is sort of the situation you find yourself in. So if I now assume fusion, how can I make this fusion process work? So in that table, you saw that the exhaust velocity coming out of the back of the spacecraft was 7.1% of the speed of light, okay? Now that coincides with, oh, wrong way, yep. Sorry. That coincides with this fusion reaction. So if I have protons on lithium-7, I get two alpha particles out, which share 17.2 MeV of kinetic energy. Okay, so if I now take that spacecraft and actually don't have, oh, so yeah, so if I go, well, you saw that picture with the big sail on the first slide. So the idea is that that big sail is a positive and negative electrostatic lens, which takes the alpha particles, which are coming off in all directions, and steers them out in toward the back as a collimated exhaust. Okay, and so the idea is that I now have those two helium nuclei. Oops. So yeah, that's the blue sail is negatively charged, the red sail is positively charged, and Grace Bittlingmeyer, who's going to give a talk tomorrow on power, she did the simulations that showed that, yes, all these alpha particles do come out, and they form a reasonable collimated exhaust. Okay, let me get caught up again where I'm supposed to be. Okay, so the idea is that you have now I'm an accelerator physicist. I've been doing that for 40 years. And so the idea is that I take the protons of the lithium-7 nuclei and I collide them, okay? And I do that in a standard, well, more or less standard particle accelerator collider that's similar to the LHC, the Tevatron, the Cordell Caesar E plus E minus machine. As a species, we've done collisions of particles a lot. We understand the drawbacks of it, and we understand the advantages and the difficulties. But it is something that, if you want to, but this is in an architecture that no one has ever even come remotely close to attempting. So in the sort of the grand Mythbusters approach to science, instead of, sitting there and doing SolidWorks simulations for 50 years and, discussing how many angels dance on a pin, just start somewhere, start building the first prototype and just get going, okay? Luckily, I have enough investors for my day job and they want me to maintain my scientific credentials and sort of not be forgotten by the scientific community, so they've given me permission to divert some of their money to work on this stuff. So that's one model of how to make progress, okay? And so the idea is that we have a sort of ephemeral particle collider that's electrostatic. The particles fall into the center. They collide at peak kinetic energy in the center. They go through each other. Most of the particles in each beam go through each other and then stop and return, and they just slosh back and forth, constantly colliding with one another. And it's ephemeral. It's composed of very thin wires, so most of the helium particles can leave in 4 pi steradian and come out and get into that sail structure. So here is actually the second prototype that we're going to have operating, but the first one we actually started construction on. So this is so you have a collision point in the center. You have ion sources on the end, which is indicated by those red disks. And you have a conical electrode structure because there's something called elastic Coulomb scattering that you will have to deal with and mitigate as if you want to make this operate and in a weird sense of break-even, achieve break-even and continuous operation. Okay, so this thing has already been built. It's under vacuum. We've already applied a ion source to it. Didn't work very well, so right now, as soon as I get back, we're going to assemble the revised ion source and get this to work. So there's a side view. It is just a big tank with lots of stainless steel, custom-made electrodes inside of it. Because we're on Earth, we need a big honky vacuum chamber, right? Okay, and the disks have to be stainless steel because there's gravity, and if having those thin wires doesn't work at 1G. Okay, so, and also because of the limitations of power supplies and the fact that people have to be around this and so on, we're actually doing DD fusion. So we're colliding deuterium on deuterium, okay? And the benefit of that is it produces a neutron, okay? Every time you get a DD fusion reaction, you get a neutron, which if you have a wall of salt blocks sitting next to that collision point, the salt absorbs and moderates and absorbs the neutrons, generates a gamma ray, which then can be detected by these large area detectors. Okay, and so we have a built-in luminosity detector that then both confirms that we're getting continuous fusion and shows that we know how to create stable beams and we know how to deal with the elastic Coulomb scattering. Okay, so inside we have a particularly shaped axial potential, and what that sort of parabola shape, that curvature of that parabola provides radial focusing, and that radial focusing then provides stability for the beam against deflections and errors and thermal noise and so on. And so it turns out that within that accelerator, there is a range of kinetic energies that will be stable. That ranges, in this case, from 31 keV to about 50 or 49.5 keV. So the center of this machine is set at negative 54 kilovolts. The ends are at ground, and so the ion sources are at ground, all the instrumentation's at ground, and then the negative voltages at the center pull the deuterons inward, and that's what gives them the kinetic energy to fuse. This is the second machine that we now are going to be operating first. The vast majority of this was actually built by Grace. So if you ever want to hire somebody who's both brilliant in mathematics and physics, but also knows how to machine and solder and every other thing you would need to do to build one of these things, give her a job after she graduates from Cornell. By the way, she did this as an undergrad. Okay, so the idea of this machine, this is also 54 kilovolts in the middle, ground at the ends, but it's a much better vacuum system. It's actually optimized for vacuum so that we can study this, those stability curves and the stability criterion at low luminosities. The bigger white collider, electrostatic collider that you saw there, that will be operated at higher and higher luminosities so as to start invoking more and more elastic Coulomb scattering and understand how to mitigate that effect. Unmanned probes versus manned missions. I'm constantly being asked, why aren't you doing manned missions? Okay, and so this is sort of a history lesson where, you know, people were flying things, objects, not people, very early in history, and, you know, it was only in, you know, the last 1,000+ years that we actually had someone survive a parachute jump. And then, you know, we had more and more of these flights. First tethered balloon flight, you know, just a couple hundred years ago. So my sort of admonishment is just be patient. This time it won't take a millennium to get between unmanned and manned missions. Thank you.
So I think the HE3 is something that like we can make pretty easily. Is the PLI-7, is that a common material? Or is that?
Lithium-7 is 95% natural abundance. Lithium-6 is 5% natural abundance. There's already lots of people who are doing separation, not in the Western world because it uses the process uses mercury, and so it's been banned. It's only done in Russia, China, and North Korea, a few other places.
Is it abundant enough that you could kind of scale that up?
Oh, there's tons of it, yeah. I mean, it's not a problem. It better not be a problem, it better not be a problem because all the tritium breeding blankets that people want for all the Commonwealth fusion and everybody else who uses DT fusion, they require enriched lithium-6 for their blankets. By the way, for instance, DT doesn't work for deceleration because with a 12-year half-life, there's no tritium left after 100 years.
I'm not quite clear on how, when there are losses and collisions and scattering that slow the ions down gradually through their multiple passages through the well, how do the ones that survive get boosted back up to the reaction speed?
Do I need to?
Do you need to? That's a good question.
Do I need to? See, because the particles started at rest at their ion source, and they pick up the kinetic energy, and they collide at that kinetic. I haven't invested any energy into those beams. In a standard tokamak or every other approach to fusion, you either have to increase the temperature of a plasma or some way invest energy into those particles. In this case, as long as when the particles fuse, they leave, then it's constantly replenishing that situation. Now, for the particles that are elastically scattered, or it would take a lot to lose that much energy if there are no electrons in this. They're nude ions. So it would take a long time, but once a particle isn't desirable anymore, you just remove it at the same kinetic, almost at the same kinetic energy that it was formed. So the dominant energy penalty is just ionization of hydrogen, right? The 13.6 eV.
How are you then changing the momentum of that fused particle? Because if you're trying to get it out of the way, if I'm envisioning this correctly, you need to push it in, some sort of orthogonal direction, right?
Well, that's the fusion, the energy released by the fusion was that 17 MeV. Okay, that's split. The two helium particles are produced back to back with equal momentum. And so they each have 9.5 MeV where they leave that collision point. Okay, and so they're self-clearing. I don't have to do anything. I just have to steer them so that they're not just going out into space in random directions where it gets zero net thrust. They have to all be redirected toward the back so that I have a net thrust or a net momentum transfer.